The universe hides secrets so strange, so alien, that even our most powerful telescopes and deepest theories cannot see them directly. But sometimes, imagination and mathematics collide to unveil a possibility so bizarre that it seems to defy the very rules we thought defined reality. Imagine a cloud, not made of water droplets, not even made of atoms, but a vast invisible presence in space that bends light, pulls stars, and curves space-time itself, without containing a single particle of matter. A cloud that exerts gravity without having mass, a structure made entirely from the very thing that causes gravity, a fog of pure force, woven from the threads of reality itself. This is not science fiction. This is the radical idea of graviton condensates, hypothetical clouds composed purely of gravitons, the elusive quantum carriers of the gravitational force. No atoms, no energy as we know it, just gravity, raw, potent, and unanchored to matter. These aren't ordinary structures. They are clouds of geometry, ghostly formations made of the very force that binds the cosmos together. They don't emit light, they can't be touched, and yet they might shape galaxies, influence black holes, and hold answers to mysteries as vast as the universe itself. But before we continue, subscribe to the channel so you don't miss out on any of these videos. What if these invisible clouds have been with us from the beginning of time, steering the evolution of galaxies, sculpting the web of cosmic structure, and mimicking the behavior of dark matter? What if the dark scaffolding that holds the universe together isn't matter at all, but concentrated gravity without substance? This is the story of graviton condensates, a breathtaking hypothesis on the bleeding edge of physics, where quantum mechanics, general relativity, and cosmic mystery blur into one. It all begins with the impossible. In our everyday experience, gravity is tied to mass. You feel the Earth pulling on you because the Earth has mass. Planets orbit stars because stars have mass. Mass warps space-time, creating the curves that bodies follow. This is Einstein's legacy. But what if there were gravity without mass? What if there was a way for the universe to generate gravitational fields that do not arise from stars, black holes, or dark matter, but from nothing more than gravity itself? It sounds like a paradox, a self-creating force, a feedback loop of pure interaction. To grasp this, we must strip away our assumptions. We're used to thinking of clouds as vapor, particles clustered together. But now imagine a cloud with no particles in the traditional sense. Instead, it's composed of the quantum units of gravity itself, hypothetical particles known as gravitons. In standard quantum field theory, forces are mediated by gauge particles: photons for electromagnetism, gluons for the strong force, the W and Z bosons for the weak interaction. And for gravity, the theory predicts the graviton. Unlike the other force carriers, the graviton has never been directly observed. It is massless, moves at the speed of light, and has a quantum spin of 2, characteristics that make it quite unlike anything we've ever detected. But if it exists, it mediates gravity in the same way photons mediate light. Now here's the twist. If gravitons can interact with one another, and if they can form coherent quantum states, then, just like atoms can form a Bose-Einstein condensate, maybe, just maybe, gravitons could condense into vast, stable quantum structures, clouds made purely of the interaction itself. Not mass, not energy, not matter, just force. These clouds would warp space, bend the paths of stars, and manipulate light not because they contain matter, but because they are gravity condensed into a stable, coherent form. This flips the traditional model on its head. Rather than gravity being the byproduct of mass, here, gravity is the object. The cloud doesn't produce gravity, it is gravity. And that changes everything. Imagine standing inside such a cloud. Not that you could see it, feel it, or know it's there, but your clocks would tick more slowly. Light would bend strangely. The paths of nearby stars would curve in unexpected ways. Entire galaxies might be cradled in its grip, spinning faster than they should, obeying an invisible master. And yet if you pointed a telescope at it, you'd see nothing. We are taught that gravity is one of the weakest forces. It takes a whole planet to pull on a paperclip with the same strength as a tiny magnet. But when you concentrate gravity into a coherent structure, no mass, just gravitons, it's no longer weak. It's focused, structured, directed. These clouds would be subtle but powerful, shaping the cosmos in ways that mimic dark matter, perhaps even replacing it entirely. Could such structures really exist? Could the universe harbor these silent behemoths, not made of matter but of curvature? Are we surrounded by clouds of invisible force, guiding the stars and shaping the cosmos from the shadows? And most haunting of all, are we inside one right now? To understand graviton condensates, we must first dive into the heart of one of the most elusive concepts in modern physics, the graviton itself. Unlike particles like the electron or the photon, which we have not only theorized but also directly detected and measured in laboratories, the graviton remains completely hypothetical. And yet the entire framework of quantum gravity rests upon its shoulders. So what exactly is a graviton? In quantum field theory, the mathematical framework that unites quantum mechanics with special relativity, every fundamental force is mediated by a corresponding particle. These mediators are known as gauge bosons. Photons carry the electromagnetic force, gluons carry the strong nuclear force, the W and Z bosons carry the weak interaction, and for gravity, the theory predicts the graviton. Unlike the other force carriers, the graviton has never been directly observed. It is massless, moves at the speed of light, and has a quantum spin of 2, characteristics that make it quite unlike anything we've ever detected. But if it exists, it mediates gravity in the same way photons mediate light. Now here's the twist. If gravitons can interact with one another, and if they can form coherent quantum states, then, just like atoms can form a Bose-Einstein condensate, maybe, just maybe, gravitons could condense into vast, stable quantum structures. Clouds made purely of the interaction itself, not mass, not energy, not matter, just force. These clouds would warp space, bend the paths of stars, and manipulate light, not because they contain matter, but because they are gravity condensed into a stable, coherent form. This flips the traditional model on its head. Rather than gravity being the byproduct of mass, here, gravity is the object. The cloud doesn't produce gravity, it is gravity. And that changes everything.
Imagine standing inside such a cloud. Not that you could see it, feel it, or know it's there, but your clocks would tick more slowly. Light would bend strangely. The paths of nearby stars would curve in unexpected ways. Entire galaxies might be cradled in its grip, spinning faster than they should, obeying an invisible master. And yet, if you pointed a telescope at it, you'd see nothing. We are taught that gravity is one of the weakest forces. It takes a whole planet to pull on a paperclip with the same strength as a tiny magnet. But when you concentrate gravity into a coherent structure, no mass, just gravitons, it's no longer weak, it's focused, structured, directed. These clouds would be subtle but powerful, shaping the cosmos in ways that mimic dark matter, perhaps even replacing it entirely. Could such structures really exist? Could the universe harbor these silent behemoths, not made of matter but of curvature? Are we surrounded by clouds of invisible force, guiding the stars and shaping the cosmos from the shadows? And most haunting of all, are we inside one right now? To understand graviton condensates, we must first dive into the heart of one of the most elusive concepts in modern physics, the graviton itself. Unlike particles such as the electron or the photon, which we have not only theorized, but also directly detected and measured in laboratories, the graviton remains completely hypothetical. And yet, the entire framework of quantum gravity rests upon its shoulders. So what exactly is a graviton? In quantum field theory, the mathematical framework that unites quantum mechanics with special relativity, every fundamental force is mediated by a corresponding particle. These mediators are known as gauge bosons. Photons carry the electromagnetic force. Gluons carry the strong nuclear force. The W and Z bosons carry the weak nuclear force. But gravity, the most familiar yet most mysterious force of them all, has no confirmed gauge boson. To bring gravity into the fold of quantum field theory, physicists propose the graviton, a massless spin-2 boson that mediates the gravitational interaction. This means, in theory, that when two objects attract each other gravitationally, they are exchanging gravitons at the quantum level. This might sound abstract, but it's no different in structure than how a magnet repels or attracts another through the exchange of virtual photons. Why spin 2? Because gravity is not just a pulling force, it is a curvature of spacetime. In Einstein's general theory of relativity, massive objects warp the very geometry of space and time, and smaller objects simply follow that curvature. When you linearize Einstein's equations, reduce them to a form where they can be compared to quantum field theory, you naturally end up with a field that behaves as if it's made of spin-2 particles. Spin is not rotation in the everyday sense. It's a fundamental quantum property that governs how particles behave under symmetry operations. The spin of 2 gives gravitons the tensor properties required to reproduce the behavior of gravity at the macroscopic level. Now here's the kicker. Gravitons, if they exist, must be massless. This is because gravity has an infinite range. Just as the photon is massless and can travel forever, making electromagnetic waves possible, the graviton would also need to be massless to allow gravity to stretch across the cosmos. If gravitons had mass, gravity would have a finite range, which is clearly not the case based on astronomical observations. But here's the problem. We've never detected a graviton, not directly, not indirectly. Why? Because gravity is incredibly weak compared to the other forces, quadrillions of times weaker. To detect a single graviton, you would need a detector so sensitive and massive that it would collapse into a black hole just by being built. In other words, the very act of trying to measure a graviton might doom the experiment by the laws of physics themselves. It's the ultimate catch-22. Yet the graviton's absence in the lab doesn't rule it out. On the contrary, its mathematical necessity in quantum gravity is profound. Numerous approaches to unifying general relativity with quantum mechanics, such as string theory, loop quantum gravity, and asymptotic safety, all rely on something that behaves like a graviton to explain how gravity works at the smallest scales. In string theory, for instance, the graviton arises naturally as a vibration mode of a fundamental string. It's not added in by hand, it just falls out of the mathematics, a ghost particle that appears when you quantize strings and let them dance through higher dimensional space. In fact, the discovery that string theory predicts a spin-2 massless particle was one of the early signs that it might be more than just a mathematical curiosity.
But the real mystery isn't just if gravitons exist, it's how they might behave in large numbers. This brings us to the tantalizing possibility of graviton condensates. If gravitons exist, and if they can interact weakly with each other, then perhaps under certain extreme cosmic conditions, they could form coherent quantum states, similar to how photons form laser beams, or how atoms condense into a Bose-Einstein condensate. This is not just a theoretical fantasy. In certain limits, high-energy graviton interactions might behave collectively. Some models suggest that black holes could be composed of large numbers of soft gravitons bound together in a stable condensate, rather than being true geometric singularities. That is, the black hole isn't a point of infinite density, it's a vast blob of overlapping gravitons behaving as one. The graviton thus isn't merely the messenger of gravity. It could be the building block of gravitational structures in its own right. If we could understand its properties, massless, spin 2, propagating at light speed, and weakly interacting, we could begin to imagine not only the foundations of gravity, but entire new phenomena built from gravity itself. Could vast crowds of these particles hover across galaxies, bound not by matter, but by mutual gravitational coherence? Could these graviton fields form something akin to a fluid, a sea of force particles rippling through space-time, shaping the cosmos without emitting light? These questions drive the frontier of theoretical physics today. Because if gravitons exist, and if they can clump together or condense, then we may be missing an entire layer of structure in the universe, hiding behind our assumptions of what mass and gravity must be. Gravitons aren't just a placeholder in quantum field theory. They may be the cornerstone of a new way of seeing reality, one where gravity isn't the consequence of mass, but an entity of its own, capable of existing, growing, interacting, and shaping the universe with or without anything material nearby. In the physics we know, gravity is born from mass. It's the most intuitive idea we inherit from everyday life. Drop a ball and it falls, pulled by Earth's mass. Planets orbit the sun because of its immense weight. Galaxies stay bound because stars collectively exert a gravitational grip. Einstein reimagined this as the curvature of spacetime. Mass tells space how to curve, and space tells objects how to move. But in all this, mass remains the trigger. No mass, no gravity. That's the classical rule, but graviton condensates spit in the face of that rule. Let's first lock in what we mean by gravity coming from mass. In Newtonian physics, the force of gravity is proportional to the product of two masses and inversely proportional to the square of the distance between them. Einstein upgraded this with general relativity, where the source of gravity isn't just mass, but energy and momentum captured by the stress-energy tensor. This includes pressure, radiation, and, yes, even light can bend spacetime because it has energy. Still, in all these formulations, something tangible that carries energy or momentum is required to cause gravity. In essence, something must exist to curve spacetime. But what if that something was the curvature itself? That's what graviton condensates propose, that gravity could generate gravity, that through quantum coherence, a cloud of interacting gravitons could become a self-sustaining entity. No matter, no photons, no atomic particles, just force, organizing itself. This is an alien concept in classical physics. We're used to fields being effects of something, a magnetic field from a current, an electric field from a charge, a gravitational field from a mass. But what if a field could become its own source, its own sustainer? In the quantum world, particles are excitations of fields, localized ripples of energy. A graviton is a ripple in the gravitational field. Now, imagine not one ripple, but trillions of them, perfectly overlapping, reinforcing, locked into a collective state. This is the concept of a condensate. In this framework, gravity isn't acting because there's a lump of mass. It's acting because a coherent pattern of force particles, gravitons, is maintaining a stable configuration that still curves spacetime. It's not that something is there that's causing gravity. The gravity is the thing that's there. Let's break the strangeness down further. Say you had a region of space devoid of all matter, total vacuum, zero-point energy only, nothing emitting light. But in that void, there's a standing wave pattern of gravitational field, made not from external sources, but from a condensate of gravitons. To a passing object, this would feel like entering a gravitational field. Light would bend, time would slow, paths of motion would shift. But telescopes, spectrometers, radiation detectors, they'd all register silence. Not because the field is weak, but because it's invisible in every way except its effect on spacetime curvature. This is not just theoretical speculation.
In fact, the idea that gravity can exist without matter is embedded in general relativity itself. Einstein's equations admit vacuum solutions, scenarios where the stress-energy tensor is zero, but curvature still exists. The most famous example? Gravitational waves. These are ripples in space-time predicted by Einstein and confirmed by LIGO. They exist and carry energy, yet require no mass to propagate. They're pure geometry in motion. If gravitational waves are the traveling form of massless curvature, graviton condensates could be the stationary form, stable patterns of geometry locked in place exerting gravitational influence without mass. One is a wave, the other is a standing pattern. One is dynamic, the other coherent. This leads to a profound implication. Gravity doesn't always need mass to exist. If graviton condensates can form, then gravity can become autonomous, not a reaction to matter, but a structure unto itself. The implications are vast. It would mean our models of galaxy formation, gravitational lensing, black hole behavior, and even cosmic expansion might be missing a key player: massless, non-luminous clouds of pure gravitational architecture. And the effects wouldn't be small. These graviton clouds could shape orbits, distort space, or bind galaxies. Their curvature of space-time could mimic the presence of dark matter, explaining gravitational effects that we usually attribute to hidden mass. In fact, they might be what we've mistaken as dark matter all along, not particles, but patterns of curvature sustained by graviton interactions. Furthermore, if gravity can exist in stable, matterless forms, then mass and gravity are not intrinsically linked. That turns one of the deepest assumptions in physics on its head. We've long believed gravity is a consequence, a side effect of stuff. But now it might be that gravity is an actor in its own right, capable of existing, growing, interacting, and shaping the universe with or without anything material nearby.
This opens the door to an even stranger vision, a universe where matter is not the fundamental scaffold, but merely a guest in a deeper realm structured by gravity alone. Perhaps mass is just a perturbation in an ocean of graviton condensates. Perhaps gravity doesn't need mass, but mass needs gravity to even define its place in the cosmos. To understand what a graviton condensate might be, we need to first explore what the word condensate even means in the realm of physics. The term doesn't just refer to water vapor turning into dew on a leaf. In quantum mechanics, a condensate is something far more exotic, more precise, and more powerful. It refers to a state of matter where individual particles, which normally behave independently, fall into lockstep, becoming a single, unified quantum system. A condensate is, in effect, many particles behaving as one. Let's start with the most famous example, the Bose-Einstein condensate. Predicted in the early 20th century by Satyendra Nath Bose and Albert Einstein, a BEC forms when a group of bosons, particles with integer spin, are cooled to temperatures so close to absolute zero that their individual identities blur. At that point, their wave functions, the quantum descriptions of their states, overlap completely. They fall into the same lowest energy level, and instead of behaving like millions of distinct particles, they act like a single, giant particle, with one shared quantum identity. In practical terms, that means bizarre things happen. Superfluidity, zero viscosity, matter that flows endlessly without losing energy, light slowed to walking pace, even matter waves that interfere like ripples on a pond. These aren't science fiction, they're observed phenomena in ultra-cold atomic gases like rubidium or sodium when cooled with lasers in magnetic traps. Another familiar example is a laser, which can be seen as a coherent condensate of photons. In ordinary light, photons scatter randomly, but in a laser, they're all in phase, moving in the same direction, at the same frequency, with the same polarization. They become coherent. The result is focused, powerful, and extraordinary. Then there are superconductors, where electrons, usually repulsive, pair up into Cooper pairs and form a condensate that can move through a lattice without resistance. Again, we see individual quantum particles losing their identity, merging into a collective behavior that transcends classical rules. Condensates are a recurring theme in advanced physics. They show up whenever nature allows particles to synchronize under the right conditions. Sometimes it's low temperature, sometimes it's high density, sometimes it's just the right interactions. The unifying idea is coherence. Individual particles in a condensate lose their separate quantum states and adopt a shared wave function. In that sense, the system becomes more than the sum of its parts. It becomes a new phase of matter governed by collective rules. So, how does this apply to gravitons? Well, if gravitons exist, and if they are bosons, which they must be due to their spin-2 nature, then they are eligible to form a condensate under the right conditions. That's the door that opens the possibility of graviton condensates, collections of gravitons all occupying the same quantum state, forming a unified gravitational structure. Now, gravitons would be massless, so unlike atoms in a Bose-Einstein condensate, they wouldn't be confined by conventional methods like cooling or trapping, but they could be confined or stabilized by gravitational self-interaction, a feedback loop where the very gravity they generate helps hold them together. This would make them very different from ordinary matter-based condensates. You wouldn't be able to chill a room to near absolute zero and produce a graviton condensate. You'd need extreme conditions of spacetime itself, maybe near black holes or in the early universe when densities and energies were off the charts, or even in the vast halos of galaxies where dark matter seems to hide. But the principle remains the same. A graviton condensate would be a macroscopic quantum object, a structure where vast numbers of gravitons lock into a coherent state, collectively curving spacetime. They wouldn't just act as individual force particles, they'd become the field. And here's where it gets fascinating. In a typical field, say an electromagnetic field, you can have random fluctuations, but once coherence is achieved, you get laser light. In a gravitational field, coherence could mean something stranger. Structured curvature, stable gravitational patterns that hold shape and influence nearby regions of space without needing matter. In fact, some physicists have suggested that black holes themselves may be graviton condensates, not singularities, but massive, self-sustaining quantum states made of overlapping gravitons. This would help resolve paradoxes like information loss and remove the need for infinities at the core. So when we talk about condensates in physics, we're talking about a new kind of order, an alignment of the chaotic, a harmony of the random. From the dance of atoms in an ultra-cold lab to the interplay of photons in a laser, nature has shown that condensates are not only possible, they're powerful. And if gravitons can do the same, then graviton condensates might be the largest, most invisible, and most influential condensates in the entire cosmos, hitting in plain sight, bending spacetime, shaping galaxies, and rewriting our understanding of gravity itself. Now that we understand what a condensate is and how graviton condensates could, in principle, be possible due to the bosonic nature of gravitons, we step into the deepest waters of theoretical physics, where speculation, advanced mathematics, and the fringes of cosmology collide.
The idea of graviton condensates lives at the intersection of quantum field theory, general relativity, and emerging frameworks in quantum gravity. While we've never detected a single graviton, we know from the structure of our best theories that if gravity is a force like the others, a quantum field, then it should, at the deepest level, be made of exchange particles. These particles, the gravitons, would be massless and weakly interacting, but that doesn't mean they can't do something extraordinary when the conditions are right. The first theoretical path to graviton condensates emerges from an idea proposed by physicist Gia Dvali and his collaborators, known as the black hole quantum N portrait. According to this model, A black hole is not a geometric singularity as general relativity suggests, but a bound state of a large number n of soft gravitons, gravitons with extremely low energy, in a Bose-Einstein-like condensate. This condensate gives rise to what we perceive as the black hole's classical gravitational field. This idea flips the traditional view on its head. Instead of gravity being shaped by an object, a black hole, the object is the collective state of many overlapping gravitational particles. These gravitons interact weakly, but because there are so many of them, n approaching numbers like 10 to the 60 or more, their collective effect becomes macroscopic and classical in nature. That's the crux of the graviton condensate theory. Even weakly interacting particles can create strong effects through sheer numbers and coherence. So where could such a thing form in the cosmos? One possibility is in the early universe, just fractions of a second after the Big Bang. At that time, temperatures and energy densities were beyond anything we can replicate in laboratories. Space-time was a churning foam of quantum fluctuations, and all four fundamental forces may have been unified. As the universe cooled, symmetries broke, and the forces separated. In that brief phase transition period, quantum gravitational states could have frozen in as stable graviton condensates, like cracks forming in ice as water freezes, only at a cosmic scale. Another candidate location is the vicinity of black holes. Near the event horizon, the boundary beyond which not even light can escape, quantum effects grow stronger, even if the black hole is large. Some models suggest that the very curvature of spacetime could cause gravitons to pile up and form standing waves. These trapped, low-energy gravitons could fall into resonance and condensation, forming a shell or core of coherent quantum gravitational energy, a graviton cloud. Likewise, cosmic strings or other topological defects predicted in high-energy theories could serve as seeds for graviton condensation. These are remnants of early universe symmetry breaking, and their immense gravitational tension could catalyze graviton interactions, especially in regions where spacetime is highly curved but matter density is low. Interestingly, dark matter halos, the mysterious invisible structures that seem to surround galaxies and hold them together, have also been proposed as possible sites for graviton condensates. These halos don't emit light, don't interact with electromagnetic fields, but have a massive gravitational influence. It's conceivable that these halos are not made of particles at all, but are large-scale graviton condensates that have stabilized into quasi-spherical distributions, sustaining themselves by their own internal gravitational coherence. Now, the elephant in the room. How do massless, non-self-interacting particles like gravitons condense at all? The answer lies in quantum gravity, and here things get more speculative. In ordinary field theory, particles interact through the fields they create. Gravitons, as carriers of gravity, should in principle interact with each other because they carry energy and momentum, and gravity couples to all forms of energy. This means gravitons gravitate. They interact with each other gravitationally. The interaction is weak, immensely so. But in environments where trillions upon trillions of gravitons are packed into a region, even weak self-interaction can become significant. Think of a gravitational analog to a photon laser. In lasers, photons don't directly interact, but the quantum medium amplifies coherence. If some underlying quantum gravitational medium exists, like the gravitational vacuum or space-time foam, it could potentially allow for graviton wave functions to overlap and lock into phase, forming a coherent condensate. Even without strong interactions, the stability of such a system would depend on the balance of inward gravitational pressure and outward dispersion, much like what happens in neutron stars or white dwarfs, but here with quantum gravity doing the balancing act. Some versions of string theory and loop quantum gravity allow for such structures. In string theory, for instance, gravitons arise as vibration modes of closed strings. Under certain conditions, large numbers of closed string modes could interact and form a condensate in a higher dimensional space. In ADS-CFT correspondence, a key idea from string theory, black holes in anti-de Sitter space are equivalent to thermal states in a dual field theory, and some interpretations suggest that these thermal states may themselves be graviton condensates.
In loop quantum gravity, space-time is quantized, made of discrete chunks. In this framework, gravitons could emerge as collective excitations of these loops. A condensate might form when a large number of loop excitations resonate in unison, forming what could be perceived as a macroscopic gravitational field. Even in speculative emergent gravity models, where gravity is not a fundamental force but emerges from entanglement or thermodynamics, graviton-like behavior could arise from underlying information networks. A graviton condensate, in that view, would be a region of space where entanglement or information flow is exceptionally coherent, producing stable gravitational curvature. Despite the diversity of these theories, they all converge on one key point. If gravitons exist, and if they obey quantum mechanics, then under certain conditions, they can condense. And when they do, they stop being merely force carriers. They become entities, structures, objects, formations of pure gravity that can shape the universe. And because these condensates are made of massless invisible particles, they would not emit light nor reflect it. They would remain undetectable by ordinary means except through their gravitational influence. So the theory of graviton condensates is not an arbitrary leap. It's a logical progression from the known behavior of quantum bosons, combined with our deep need to unify quantum mechanics and gravity. It's a speculation, yes, but one grounded in the mathematics of fields, the nature of quantum states, and the desperate need to explain cosmic structures we still do not understand. It tells us that there may be objects in the universe, not made of matter or energy in the traditional sense, but made entirely of organized, coherent geometry. When we hear the word cloud, especially in the context of physics or astronomy, we tend to imagine something diffuse, vaporous, fluffy, gentle, a wisp of particles drifting silently in the void. But if we continue thinking of graviton condensates as mere clouds, we risk drastically underestimating what they really are. These are not delicate passive drifts of force particles. They are potentially the most concentrated and structured forms of gravity that can exist without matter. Rather than ephemeral fog, graviton condensates might be dense, self-sustaining, and profoundly organized quantum structures. Not built from atoms or energy in the conventional sense, but built from curvature, coherence, and quantum geometry. They are structures of force, shaped not by mass, but by the collective, synchronized interaction of billions upon billions of massless force carriers, gravitons, locked in perfect phase like the components of a cosmic machine. Let's start with an analogy. Think of a laser. To the naked eye, it seems like a simple beam of light. But under the hood, it's an incredibly structured, coherent system. The photons inside a laser are all identical, the same energy, the same direction, the same phase. This coherence allows the laser to do things ordinary light can't: cut through steel, bounce over vast distances without dispersing, or encode vast amounts of data. Now take that idea, but replace photons with gravitons, and light with curvature itself. You don't get a flashlight made of gravity, you get a space-time formation, a dense knot of structured gravitational influence. A region of space where curvature isn't simply reacting to mass or energy, it is being generated, sculpted, and sustained from within. The structure is not fluffy, it is tight, organized, persistent. This isn't just theoretical poetry. In several speculative models, including quantum end-portrait theories, classical field approximations, and aspects of emergent gravity,
The idea is that graviton condensates could form compact objects, far denser and more stable than traditional expectations for force-only systems. Some physicists even propose that graviton condensates could mimic the gravitational behavior of black holes, exhibiting event horizon-like characteristics without ever forming a singularity. Instead of a point of infinite density, the object would be a coherent gravitational field structure, a macroscopic quantum state made of gravitons. These structures could be just as compact as black holes, but without the paradoxes of information loss or singularity breakdown. In this picture, space-time doesn't collapse, it organizes. And it doesn't stop at black hole scales. On galactic and intergalactic scales, graviton condensates could span thousands of light years, yet maintain coherent gravitational fields. Imagine vast spherical regions enveloping galaxies, like halos, not made of dark matter, but of structured, condensed gravity itself. These would not just passively float, they would anchor stars, regulate orbital velocities, and guide the evolution of galactic arms, all without emitting a single photon. Their influence would be unmistakable, yet their presence entirely invisible to traditional telescopes. This idea is especially compelling because it provides a possible explanation for anomalies in galactic rotation curves, the strange observation that stars far from the galactic center move faster than they should based on visible mass alone. Normally, we attribute this to an unseen halo of dark matter. But what if the halo isn't matter at all? What if it's a structure of gravitational force, stable, persistent, and built from condensed gravitons? These force structures might also extend along the cosmic web, the filamentary scaffolding of the universe that connects galaxies into larger superclusters. Where we see gravitational binding but no corresponding mass, graviton condensates could be the culprit. Long, thread-like condensates of curved space winding invisibly across the void. And these wouldn't be static objects. Graviton condensates might be dynamic, oscillating gently, responding to external gravitational fields, perhaps even merging with one another. Two graviton condensates interacting could produce interference patterns in space-time itself, detectable maybe as subtle gravitational lensing anomalies or unexpected gravitational waveforms. Crucially, these aren't just waves in a field, they are macro-scale manifestations of quantum structure. They're like gravitational crystals, internally ordered, phase-locked, and robust. They might form lattice-like standing waves, create zone boundaries, or even sustain internal modes like vibrational states which echo across space-time. Let's also address density. While we often associate density with mass, in this context, gravitational density could mean the degree to which space-time curvature is organized and reinforced. A graviton condensate may be dense, not because it contains more particles per volume in a classical sense, but because it represents a higher concentration of gravitational coherence, tighter waves, more unified phase, stronger geometric effects. The density of a graviton condensate could determine how steeply it curves space-time, meaning it could be responsible for the gravitational strength in a region independent of matter. This idea breaks the usual association between mass and gravitational pull. In effect, you could have two equal-strength gravitational wells, one caused by a mass and the other by a graviton condensate, and they would be indistinguishable in their gravitational influence, but completely different in structure. This opens the door to entirely new classes of cosmic objects. We might categorize them not by what they're made of, but how they shape gravity. Imagine classifying objects as mass-bound, energy-bound, or geometry-bound, with graviton condensates occupying the third category. They would represent pure geometry objects, arising not from matter, but from organization in space-time itself. This also challenges our intuition about what's empty. A region that appears as a vacuum, devoid of stars, gas, or radiation, could actually be a knot of gravitational structure silently governing the motion of stars and galaxies. We would see its effects in how light bends or how objects move, but never observe it directly. It would be a shadow made not of absence, but of structured curvature. In this sense, graviton condensates aren't clouds. They are skeletons of gravity, scaffolds of quantum force, invisible yet indelibly written into the architecture of the universe.
To truly appreciate the radical nature of graviton condensates, we must confront one of the most profound and persistent challenges in all of theoretical physics: the unification of quantum mechanics and general relativity. This isn't just an academic puzzle, it's the deep chasm that divides our understanding of the very small from the very large, of atoms and particles from stars and galaxies, of electrons from black holes. On one side of this chasm sits quantum mechanics, the most accurate and successful theory ever devised to describe the microscopic world. Governed by uncertainty, probability, wave functions, and discrete quanta, it excels at explaining the behavior of particles, atoms, and forces. It's where gravitons belong. If they exist, they would be quantum force carriers, fitting neatly into the language of quantum field theory. On the other side is general relativity, Einstein's geometric masterpiece. It's the theory of gravitation, describing how mass and energy curve spacetime and how this curvature dictates the motion of objects. It's smooth, continuous, and deterministic. It explains everything from planetary orbits to the expansion of the universe, from time dilation to the warping of light near a black hole. But here's the catch. These two frameworks are fundamentally incompatible. Quantum mechanics deals with probability amplitudes and discrete quantities. General relativity deals with continuous differentiable manifolds of spacetime. Quantum fields fluctuate. Spacetime, in general relativity, is a smooth fabric. But what happens when you need to describe quantum fluctuations of spacetime itself? What happens near the singularity of a black hole, or at the birth of the universe where gravitational fields are at their most extreme and quantum effects are unavoidable? This is where the need for a quantum theory of gravity arises, a theory that doesn't just treat gravity as a classical field, but as a quantized force, just like electromagnetism or the strong force. The graviton is the bridge, the hypothetical quantum of the gravitational field. If it exists, it allows gravity to be treated within the quantum framework. But so far, all attempts to create a fully consistent theory of quantum gravity have run into roadblocks. One approach is to quantize general relativity directly, treating the metric, the mathematical object that describes spacetime, as a quantum field. This leads to a model where gravitons are fluctuations in this quantum spacetime. But this approach runs into trouble. It's non-renormalizable, meaning that the infinities that arise when you calculate interactions cannot be tamed or canceled out. In simple terms, the math breaks down at high energies. Another approach is string theory, which doesn't treat particles as points, but as one-dimensional strings. In string theory, the graviton appears naturally as a vibration mode of a closed loop string. This offers a promising route because string theory is finite and well-behaved, at least in the right conditions. But string theory requires extra dimensions, supersymmetry, and a vast landscape of possible universes, making it hard to connect directly to observations. There's also loop quantum gravity, which takes a very different tack. Instead of quantizing fields on spacetime, it quantizes spacetime itself, breaking it down into discrete loops or networks. In this framework, space is granular at the smallest scales, like a quantum fabric. Gravitons would then emerge as collective excitations of this deeper geometry. Loop quantum gravity is mathematically rigorous, but still acts a unifying picture that links it smoothly to the classical world of general relativity. Other approaches include asymptotic safety, causal dynamical triangulations, twistor theory, and even more radical ideas like emergent gravity, where spacetime and gravity aren't fundamental at all, but arise from quantum entanglement or thermodynamic processes. Despite the diversity of these models, they all aim at the same goal: a consistent quantum description of gravity that reduces to Einstein's theory in the classical limit, but remains valid at the Planck scale, the realm of black holes, the Big Bang, and possibly graviton condensates. This is where graviton condensates become especially interesting. They may be the intermediate language between the quantum world and the geometric world. Think of them as the bridge dialect, quantum in origin, but manifesting as classical-looking gravitational fields.
A graviton condensate could behave like a classical gravitational object, curving spacetime while being fundamentally quantum, built from coherent graviton states. This dual nature offers a powerful avenue for unification. If we can describe condensates with quantum field theory, but observe their gravitational effects with general relativity, then perhaps we are seeing two views of the same object, one from each side of the chasm. In this sense, graviton condensates might not just be exotic objects in the universe, they could be the very testing ground where quantum mechanics and gravity finally learn to speak the same language. Take the case of a black hole again. In classical general relativity, it's a singularity, an infinitely dense point surrounded by an event horizon. But in a graviton condensate model, a black hole is a large end state of soft gravitons, where the horizon is just the edge of quantum coherence. This removes the singularity, allows information to be preserved, potentially solving the black hole information paradox, and creates a smooth crossover from quantum to classical. Moreover, this idea aligns with holographic principles, such as those in the ADS-CFT correspondence, where gravity in a bulk space is dual to a quantum field theory on the boundary. If graviton condensates can be described both in the bulk and at the boundary, then they might be the manifestation of this duality, observable in both frameworks. And let's not forget cosmology. In the early universe, quantum fields were fluctuating in a background of rapidly changing spacetime. Tiny quantum variations became the seeds of galaxies. If graviton condensates existed then, perhaps as stable quantum gravitational objects, they could have had profound influence on structure formation. They might even offer clues to the quantum nature of inflation, or the resolution of the initial singularity.
In the end, graviton condensates might not just be curious structures. They might be the first true experimental fingerprints of quantum gravity, hiding in plain sight. If we could find them, study them, and model their behavior, we could finally begin to weave quantum mechanics and general relativity into a single fabric, not just mathematically, but observationally. They could be the Rosetta Stone physics has been waiting for, a gravitational structure that behaves quantumly, and a quantum structure that curves space. If graviton condensates exist, the next natural question becomes, where would such exotic structures actually form? Unlike ordinary matter-based condensates that require low temperatures and high densities in laboratory settings, graviton condensates would need extreme conditions on a cosmic scale, where quantum gravity effects could dominate, and where massive coherence could take root despite the weakness of the gravitational interaction. Let's begin with the early universe, a prime candidate for the birthplace of graviton condensates. Just moments after the Big Bang, the universe was unimaginably hot, dense, and energetic. It was a churning sea of raw quantum fields, violently fluctuating across the newborn spacetime fabric. In this primordial chaos, all fundamental forces may have been unified. Gravity, electromagnetism, the strong and weak nuclear forces all merged into a single superforce, according to grand unified theories. As the universe expanded and cooled, these forces froze out, separating and taking on their individual identities in a series of symmetry-breaking phase transitions. These transitions weren't always smooth. They could have left behind residual quantum states, much like how imperfections form in a crystal when water freezes rapidly. These imperfections might be topological defects, gravitational solitons, or, most intriguingly, graviton condensates. Essentially, the cooling of the early universe could have locked in regions of gravitational coherence that remain stable even today. Because the gravitational field pervaded the entire early cosmos, these condensates could be spread across vast regions, like relic gravitational fields, coherent zones of curvature surviving from a quantum gravitational epoch. They might even have played a role in seeding large-scale structure, forming the gravitational skeleton around which matter later clumped to become galaxies and clusters. Another key formation site is near the boundaries of black holes. In classical general relativity,
The edge of a black hole is the event horizon, the point of no return for matter and light. But this region is also where gravity is strongest and quantum effects become significant. According to certain models, particularly those involving the black hole end portrait, a black hole isn't a singularity wrapped in an event horizon, but a condensate of a vast number of soft, low-energy gravitons. In this view, the event horizon is not a sharp boundary, but a coherent surface, where the overlapping wave functions of countless gravitons form a stable, self-sustaining structure. These condensates could extend just outside or just inside the classical event horizon, replacing the idea of a singularity with a dense quantum state of pure gravity. Even more compelling is the idea that graviton condensates could form in stages, initially as quantum fluctuations near the Planck scale, then as stable gravitational modes trapped by the intense spacetime curvature near the black hole. Once enough gravitons accumulate and synchronize, the condensate becomes self-sustaining, growing in strength and size, potentially stabilizing the black hole interior and helping to resolve long-standing paradoxes about information loss and the nature of singularities. Then we arrive at the most subtle and perhaps most transformative possibility in modern cosmology: graviton condensates as an alternative explanation for dark matter halos. For decades, scientists have grappled with an enormous discrepancy between what we see in the universe and what we feel. Galaxies spin too fast. Galaxy clusters hold together too tightly. Gravitational lensing, the bending of light by gravity, is stronger than it should be based on visible matter alone. The traditional solution? Dark matter, an invisible, undetectable form of matter that interacts gravitationally but not electromagnetically. It neither emits, absorbs, nor reflects light. It remains frustratingly the most successful failure in physics.
Enter graviton condensates, a bold alternative that doesn't invoke unknown matter at all, but instead reimagines gravity itself as the hidden actor behind these mysterious effects. What if the extra gravitational pull we attribute to dark matter isn't from mass we can't see, but from fields we haven't considered, coherent structures of pure gravity formed from synchronized clouds of gravitons? Let's unpack this revolutionary idea. Imagine a typical spiral galaxy. According to Newtonian physics and even Einstein's general relativity, stars on the outer edge of the galaxy should orbit slower than those near the center, where most of the visible mass resides. But observations show the opposite: flat rotation curves, where stars far from the galactic center move just as fast or even faster than expected. The implied mass distribution doesn't match the light distribution. Something is providing gravitational support in those outer regions. In the dark matter paradigm, this discrepancy is explained by a halo of invisible mass extending well beyond the galaxy's visible disk. These halos are assumed to be made of cold, non-relativistic particles, so-called cold dark matter, that clump under gravity but remain invisible. But here's the twist. What if the halo is real, but it's not made of particles? What if it's made of structured, self-coherent gravitational fields, graviton condensates that envelop galaxies, shaping their rotation curves and gravitational behavior, all without invoking any new form of matter? These gravitational field structures would be vast, invisible, and stable. They would exert gravitational influence just like a mass halo, bending spacetime and guiding stellar motion. But rather than being composed of undiscovered particles, they would be composed of phase-locked, low-energy gravitons, forming a coherent condensate. This explanation could account for flat rotation curves, because the graviton condensate provides an additional gravitational potential well, particularly strong in the galaxy's outer regions. Gravitational lensing anomalies. Since spacetime would still curve under the influence of the condensate, light passing through these regions would bend more than expected even in the absence of visible mass. Stability of galaxies and clusters. The condensates could extend beyond individual galaxies, binding entire clusters together through large-scale coherent gravitational structures. Lack of interaction with light. Since gravitons don't couple to the electromagnetic field, their condensate wouldn't glow, absorb, or scatter light, perfectly matching dark matter's invisibility. The potential elegance of this approach lies in its minimalism. It doesn't add new particle species or new forces. It simply takes the known structure of gravity, quantum gravitons, bosons capable of condensation, and asks, could their coherent behavior mimic unseen mass? In this light, graviton condensates don't just explain dark matter halos, they are the halos. The discrepancy between visible matter and gravitational influence becomes not a mystery of missing stuff, but of misunderstood structure. We've been assuming the extra gravity is sourced by hidden mass, when in fact it might be sourced by pure gravitational architecture, invisible but deeply real. This interpretation could even explain why we haven't detected dark matter particles. If they don't exist, if the gravitational anomalies are caused by structured spacetime rather than new matter, then every experiment looking for WIMPs, axions, or sterile neutrinos is searching in vain. The solution isn't more matter, it's more gravity. Moreover, this framework could help explain the diversity of dark matter behavior across different systems. Some galaxies, for instance, appear to lack dark matter. Others seem dominated by it. If dark matter were a particle, such variation would be hard to explain. But if graviton condensates form based on local spacetime geometry or historical galactic mergers, then such diversity would make sense. Each condensate would be shaped by its environment, its past, and its gravitational resonance. Even more compelling is that graviton condensates might naturally produce chord halos, where gravitational influence is spread smoothly rather than clumping in a dense center, matching what's observed in low surface brightness galaxies better than cold dark matter simulations, which often predict overly cuspy centers. And since condensates are quantum in nature, their structure could resist collapse, providing internal pressure without temperature or thermal motion, something dark matter particle models struggle to replicate. They might even oscillate or exhibit interference effects, leaving subtle patterns in gravitational lensing data that no particle model would ever predict. Of course, this theory doesn't come without questions. Can graviton condensates form quickly enough in the early universe to seed galaxy formation? Would they remain stable for billions of years? Could they account for all gravitational anomalies across scales, from dwarf galaxies to galaxy clusters to the cosmic microwave background? Those are open questions, but they're no more speculative than the idea that trillions of invisible particles pervade the cosmos, never interacting with light or one another in any detectable way. In fact, graviton condensates offer an economical and testable alternative. They tie the mystery of dark matter to the known, or at least theoretically expected, properties of gravity itself. In the end, the concept is stunningly simple. We may not need new stuff to explain the universe. We may just need to understand how the old stuff organizes itself, how gravity at quantum scales can take on forms we've never seen, never measured, but that have been there all along, shaping galaxies like invisible hands sculpting stars. One of the most perplexing observations in modern astrophysics is the existence of galaxies that spin far faster than they should, given the amount of visible matter they contain. When astronomers map out the distribution of stars, gas, and dust in galaxies, and then calculate how fast these components should orbit the galactic center using Newtonian dynamics or Einstein's general relativity, the results come short. There simply isn't enough mass to account for the observed rotational speeds, especially in the outer regions of galaxies. These anomalously high orbital velocities were one of the original smoking guns that pointed toward the existence of dark matter. The idea was simple. If visible matter isn't enough, there must be invisible matter adding to the galaxy's gravitational pull, a ghostly halo of mass we can't see but that holds everything together. But what if this missing mass isn't mass at all?
What if the extra gravitational pull isn't coming from particles, but from structures of gravity itself? This is where the theory of graviton condensates offers a radical but elegant explanation. These condensates, made from coherent clouds of hypothetical massless gravitons, could generate real gravitational fields without requiring any conventional matter. And they could be present in the exact regions where these galaxies need more gravity to hold themselves together. Let's consider the rotation curves of spiral galaxies. In a purely Newtonian or Einsteinian framework, the velocity of stars should drop off with distance from the galactic center. Much like planets in the solar system orbit slower the farther out they are. This is because the mass of the galaxy is mostly concentrated in the luminous disk and central bulge. But observations tell a different story. Beyond a certain point, the rotational speed of stars levels off. It doesn't decline. The stars orbit the galactic center at nearly constant speed, even at distances where the visible mass is negligible. This flatness of rotation curves is so common and consistent that it forms the basis for empirical models of galaxy structure. But again, it requires the presence of something more, something gravitationally significant but unseen. Graviton condensates offer an alternative explanation. Imagine a halo-like structure of graviton coherence surrounding the visible galaxy. This structure doesn't emit or reflect light, but it amplifies the galaxy's gravitational pull. It's not just a cloud of extra field strength, it's a coherent quantum state shaped and stabilized by space-time curvature and the synchronized behavior of countless soft gravitons.
The beauty of this model is that it naturally reproduces the non-Keplerian dynamics we observe, stars orbiting too fast at the edges of galaxies yet staying bound in place. Instead of invoking some exotic, non-baryonic matter particle that floats around undetected, the graviton condensate model simply reorganizes gravity in a way that explains what we see. Let's take this further. Some galaxies show even more extreme discrepancies between their visible mass and their rotational speeds. There are ultra-diffuse galaxies, large in size but faint in light, which spin quickly despite having very little visible material. In traditional dark matter models, this is awkward. Why would so much dark matter collect around so little ordinary matter? But if graviton condensates are involved, the question flips. These galaxies may have formed within regions of pre-existing gravitational coherence, places where the fabric of space-time was already shaped by a graviton condensate. The baryonic matter, stars, gas, and dust, may have simply settled within these condensates, rather than the other way around. This suggests a new cosmological model: gravity first, matter second. In this view, some galaxies are not the cause of their own gravitational fields, but rather the beneficiaries of gravitational structures that formed early in the universe, condensates that predated and perhaps even seeded the formation of visible galaxies. There are also galaxies like NGC 1052-DF2 and DF4, which have been described in recent studies as having very little dark matter, an anomaly under current models. Their stars move more slowly than expected, but in the graviton condensate framework, this makes sense. These galaxies may have formed outside of a graviton condensate structure, in regions where coherent gravitational fields are weaker and rotation curves behave more classically. The graviton condensate model thus offers a unified explanation for the full diversity of galactic behavior: galaxies with flat rotation curves, enveloped in strong graviton condensates; galaxies with extreme rotational speeds and little visible mass, formed inside powerful condensate regions; galaxies with unexpectedly low speeds, lacking condensate influence, formed in gravitationally quiet zones. This framework is also scale independent. It doesn't require that each galaxy have the same amount or distribution of dark matter particles. Instead, each galaxy's gravitational structure depends on the local coherence of the graviton field, which could vary depending on cosmic history, proximity to other structures, and fluctuations in the early universe. Moreover, graviton condensates provide a physical mechanism for how galaxies maintain rotational stability. In traditional models, dark matter halos are just there, a placeholder for missing mass. But in the graviton condensate picture, the halo is dynamic and alive, a coherent gravitational field that can oscillate, evolve, and potentially interact with other fields.
It's not just an explanation, it's a prediction engine. This could lead to observable consequences. Graviton condensates might produce subtle distortions in the orbits of stars or phase shifts in gravitational wave signatures. They might even affect how galaxies respond to mergers or how their rotation curves evolve over time. These effects could eventually be detected by next-generation observatories, offering a way to test the model directly. In summary, graviton condensates offer an elegant and theoretically grounded explanation for galaxies that appear to spin without enough mass. By replacing the concept of invisible matter with that of invisible geometry, they challenge our deepest assumptions about gravity and provide a fresh lens through which to view the cosmos. If graviton condensates are real, and if they act as the hidden engines behind much of the universe's gravitational architecture, then the next question becomes deeply structural. Do they clump like matter, or do they behave in entirely different ways? This is more than a curiosity. It strikes at the heart of how the universe forms its grandest structures, from galaxies and galaxy clusters to the sprawling cosmic web that links them across hundreds of millions of light years. Let's first consider how matter behaves under gravity. Matter, because of its mass, attracts other matter. Under the influence of gravity, dust forms rocks, rocks form planets, planets orbit stars, and stars orbit in galaxies. Matter clumps because it experiences gravitational attraction and friction, and because it can cool down, losing energy and settling into compact forms. Dark matter, as we currently model it, also clumps, though in more diffuse ways. It doesn't interact electromagnetically, so it doesn't radiate or collide like normal matter. But it still forms halos and filaments, drawn together by mutual gravitational attraction, shaping the large-scale skeleton of the cosmos. So what about graviton condensates? If we imagine a cloud made entirely of massless, quantum-coherent gravitons, does it have the same tendency to gather and form dense objects? Would it build up in halos, stream along cosmic filaments, or instead remain smeared across space like a fog of structured gravity? The answer is likely more nuanced than a simple yes or no, and it depends on the quantum behavior of the condensate, the geometry of spacetime, and the coherence conditions required for such a structure to remain stable. First, graviton condensates aren't matter. They don't behave like particles with rest mass, and they don't experience the usual dissipative processes that allow matter to cool and contract. Instead, they're structures of geometry itself, built from graviton modes that reinforce each other through quantum coherence. This means their clumping behavior would not be due to gravitational collapse in the conventional sense, but rather to the stabilization of phase-coherent regions of space-time curvature. This has profound implications. Rather than clumping like matter into dense cores, graviton condensates might prefer to form extended, smoothly varying fields, like standing waves in spacetime. These resemble spherical shells, toroidal structures, or even filamentary strings of gravitational influence, configurations that maximize coherence while minimizing destructive interference. In such a framework, graviton condensates could mirror the cosmic web, not by aggregating mass, but by channeling gravitational potential across vast distances. Imagine gravitational highways, invisible scaffolds on which galaxies ride, not pulled together by particle interactions, but guided by phase-locked gravitational geometry. These structures would likely resist fragmentation. Unlike matter, which can collapse under its own gravity, graviton condensates could maintain shape due to their quantum structure, much like a Bose-Einstein condensate resists collapse until a critical threshold is exceeded. The condensate might even exhibit repulsive behavior under certain configurations, analogous to how certain quantum fluids resist compression. However, it's also possible that graviton condensates could merge, similar to how gravitational waves interfere constructively. When two coherent regions overlap with compatible phase and frequency, they could enhance one another, forming a larger, more powerful structure. This would allow gravitational halos to grow over time, not by clumping in the matter sense, but by phase resonance, creating larger domains of influence. This kind of behavior could produce non-uniform distributions of graviton condensates across the cosmos, stronger in some regions, weaker in others. Some galaxies might find themselves embedded in massive graviton condensate wells, leading to enhanced rotational velocities and stronger gravitational lensing. Others, in more diffuse regions, might rotate more slowly or exhibit less gravitational binding. Moreover, these structures could intersect, just as cosmic filaments do. Where two condensate filaments cross, the overlapping gravitational field might be stronger, encouraging the formation of galaxies and clusters. This could offer a new explanation for why galaxies form where they do, not merely at intersections of dark matter filaments, but at nodes of gravitational coherence, where gravitational geometry converges. And what about cosmic voids, vast regions with few galaxies and even less visible matter? In the graviton condensate picture, voids might be regions of decoherence, where gravitational phase alignment has broken down, leaving a gravitationally quiet zone. The absence of coherent graviton structures in these regions might explain their lack of mass and slower cosmic evolution. Another fascinating aspect is the potential feedback between graviton condensates and ordinary matter. As baryonic matter falls into gravitational wells shaped by condensates, it might reinforce the field, anchoring the condensate more deeply into the geometry of space. Conversely, energetic events like supernovae, black hole mergers, or violent galactic collisions might disrupt local coherence, causing condensates to fragment or reorganize.
In this sense, graviton condensates don't simply mirror matter behavior. They engage in a dynamic dance with matter, guiding and responding to the universe's structural evolution over billions of years. Now, let's consider simulations. In standard cosmology, simulations of structure formation rely on cold dark matter particles, which cluster and merge over time. But what would a simulation of graviton condensate-driven evolution look like? It would require modeling nonlinear quantum gravitational fields on cosmological scales, a massive computational challenge. Instead of treating mass as the source of curvature, you'd simulate the coherence of graviton wave functions, watching how they organize, interfere, and stabilize. Such simulations might produce different cosmic web patterns or predict alternative galaxy distributions, particularly in the outskirts of clusters or along filamentary bridges. And because condensates are inherently quantum, they might produce subtle interference effects, perhaps even visible in the cosmic microwave background or gravitational wave backgrounds, faint, large-scale patterns hinting at structured gravity without mass. In short, graviton condensates would not clump like matter. They would instead form coherent gravitational architectures, smooth, large-scale patterns of space-time curvature, subtly guiding the growth of galaxies, stars, and planets without ever being seen. They would shape the cosmic web not by density, but by coherence, creating a universe where gravity is not just a reaction to matter, but a structure in its own right. To truly grasp the surreal nature of graviton condensates, one must set aside the familiar notion of matter and think in terms of something far more abstract, a sea of pure geometry. Unlike atoms or particles, which possess mass, charge, and occupy discrete positions in space, graviton condensates are not objects in space, they are configurations of space itself. This is where the concept becomes truly mind-bending. Imagine a vast region of the universe where no ordinary matter exists, no dust, no stars, no particles at all. And yet, if you were to pass through this region, you would feel something, a tug, a pull, a shift in your trajectory. Your clock might tick differently, and your path through space would subtly bend. These changes would not come from any invisible substance, but from space-time itself being shaped and warped, not by mass, but by pure gravitational coherence. Graviton condensates would be entirely massless in a conventional sense. They would not have any rest energy that you could tap or any substance you could touch. They would not reflect or absorb light. They would not carry charge or decay products. But they would curve space-time and therefore influence motion, time, and light. This makes them different from everything we typically associate with stuff in the universe. To understand this, think about the way general relativity describes gravity. Einstein's equations don't treat gravity as a force in the Newtonian sense, but as curvature of spacetime. Matter tells spacetime how to curve, and curved spacetime tells matter how to move.
But what if the curve exists without matter? What if space-time itself, by virtue of coherent, quantum-level graviton behavior, organizes into regions of persistent curvature? That's what graviton condensates would be. Localized distortions in the fabric of space-time, not caused by matter, but by a self-sustaining configuration of gravitons. These regions would be pure geometry, shaped not by the presence of stuff, but by the patterns of geometry itself, like a whirlpool in a river that exists not because of debris or rocks, but because of the flow of the water itself. In this sense, graviton condensates wouldn't be things in the traditional sense. They would be topological structures, stable patterns of curvature and coherence, persisting through space-time the way a vortex persists in a turbulent fluid. And like vortices, they might move, interact, merge, or dissipate, not as particles, but as ripples of structured gravitational influence. Some physicists have drawn analogies between graviton condensates and solitons, stable, non-dispersive wave packets that maintain their shape over long distances and times. Others have suggested they might be similar to geons, gravitational electromagnetic entities first proposed by John Wheeler, made entirely from self-trapped fields. But graviton condensates go further. They are gravitational entities made entirely of gravitational quanta, warping space not from within, but from within. Visualizing such a structure is difficult, but not impossible. Imagine a vast transparent sphere, hundreds of thousands of light-years across. From the outside, it looks empty, a void. But inside, light bends slightly. Time flows differently. A star entering the region feels a gravitational pull not toward a point, but toward the structure of the region itself. This isn't due to mass at the center. There is no center. Instead, the entire region is the gravitational source, a gentle but pervasive distortion of space-time that doesn't arise from any particle or energy, but from the coherent dance of gravitons in quantum unison. In this way, a graviton condensate acts like a gravitational lens with no lensing mass, a curvature in space-time with no classical origin. It doesn't have a density in the way matter does, but it has a shape, a geometry, a field structure that defines its influence. This also means graviton condensates are entirely unbound by the usual limitations of thermodynamics. They don't need temperature to stabilize. They don't need pressure or tension. Their existence arises from quantum field coherence, not from any mechanical balance. They are waves of geometry frozen into place, like standing ripples on a cosmic pond, persistent, invisible, but undeniably real. And they may not be entirely static. Like any quantum system, graviton condensates could exhibit vibrational modes, internal excitations, or even quantum fluctuations. In extreme conditions, such as near merging black holes or during early cosmic inflation, they might oscillate or fluctuate, giving rise to measurable phenomena like gravitational wave echoes, anomalous lensing, or even subtle time dilation effects.
In fact, if our solar system were passing through such a sea of pure geometry, a massive but invisible graviton condensate, we might not know it directly. Our instruments would register no mass, no light, no radiation. And yet, if we measured carefully enough, we might see tiny deviations in the orbits of planets, anomalous drifts in spacecraft trajectories, or inconsistencies in the timing of pulsars and other cosmic clocks. Ultimately, this vision of graviton condensates leads us to a radical conclusion, that the universe may be filled not just with matter and energy, but with shapes, invisible structures of space and time, forming a hidden architecture upon which galaxies grow and stars drift. These shapes are not built from atoms or particles, but from pure gravitational rhythm, from the way space-time bends and loops and twists in response to nothing but its own quantum nature. In this cosmic ocean, we do not drift through emptiness, but swim through waves of geometry, some soft, some sharp, some vast, some localized.
It is a universe where gravity is not just a response to matter, but a sculptor of its own canvas. When it comes to graviton condensates, vast invisible regions of warped spacetime composed entirely of coherent gravitational quanta, one of the most intriguing and consequential questions is, how do they interact with ordinary matter? If they have no mass, no charge, no interaction with the electromagnetic field, and yet they shape spacetime itself, then how might they subtly affect the familiar components of the universe, stars, gas clouds, planets, even us, without ever being directly detectable through light? This is where the ghostly elegance of graviton condensates becomes apparent. Their influence would be gravitational only, and yet that might be more than enough to leave an indelible imprint on the evolution of the cosmos. To begin with, consider how normal matter responds to gravity. A star doesn't need to see gravity, it simply follows the curvature of spacetime around it. Gravity acts not through contact, but through geometry. So if a graviton condensate alters the geometry of the region it occupies, even subtly, it will cause normal matter to move differently than it would in flat, unperturbed spacetime. Take a star orbiting near the edge of a galaxy. In the absence of a graviton condensate, its orbit should slow and fall off as you move away from the galactic center. But if the star moves through a region influenced by a graviton condensate, even one with no mass whatsoever, the gravitational field created by the condensate could maintain the star's orbital velocity or even accelerate it. This wouldn't require the star to interact with the condensate directly, but simply to obey the curved geometry established by the condensate's quantum structure. In other words, a graviton condensate could cause stars to move as if there were extra mass present, even though there's nothing to see. This is precisely what we observe in galaxies all over the universe, stars behaving as if something invisible is tugging on them. Now consider gas clouds, the vast interstellar clouds of hydrogen, helium, and dust from which stars are born. These clouds are extremely sensitive to gravitational environments. Even a small deviation in the local potential can affect how the gas compresses, cools, and collapses. A graviton condensate would act like an invisible gravity well, nudging the gas into denser clumps, potentially triggering star formation, or conversely, stabilizing it and preventing collapse. In fact, in regions rich with gas but with no obvious gravitational anchor, the presence of a graviton condensate could explain anomalous star formation. Stars emerging in the apparent absence of sufficient matter to gravitationally bind the gas. It could also explain the suppression of star formation in seemingly ideal conditions if the gravitational field is warped in a way that resists gas compression. Another profound effect would be on orbital dynamics. Consider objects like satellites, moons, and planets. If Earth, for instance, were embedded in a weak graviton condensate, say part of a larger galactic-scale condensate structure, its orbit around the Sun might appear slightly altered over very long timescales. These changes would be tiny, perhaps only measurable in pico or femto arcsecond shifts, but in principle detectable with next-generation astrometry missions. More dramatically, if a binary star system were partially embedded in a graviton condensate, we might see irregularities in their mutual orbits, perhaps an unexplained precession, a time-varying orbital period, or a deviation from expected gravitational wave emission rates. These are the kinds of anomalies that might be currently dismissed as noise, but in the graviton condensate framework, they could be the whispers of pure gravity architecture. Even cosmic rays and high-energy particles might show subtle path deflections when traveling through regions of spacetime shaped by graviton condensates. Again, the effect would not come from scattering or collisions, but from the bending of their trajectories due to curvature alone. One particularly fascinating possibility is the influence of graviton condensates on light travel time. Although they don't absorb or reflect light, condensates curve spacetime, which means that photons passing through them would experience gravitational time dilation and path deviation. A light beam traveling across a condensate might arrive slightly earlier or later than predicted, or appear to bend in an unexpected way, leading to anomalous lensing patterns with no visible mass to account for the distortion.
This opens the door to a new class of gravitational lensing phenomena, lensing without lensing mass. Observatories might detect light being bent or magnified in regions of empty space, areas where no galaxy or cluster exists. These might be the locations of graviton condensates, distorting spacetime in subtle but measurable ways. There's also the possibility that graviton condensates could interact with gravitational waves themselves. As ripples in spacetime move through a region structured by a graviton condensate, they might be distorted, delayed, or even scattered in a way that reveals the presence of an underlying quantum gravitational field. This could create echoes, dampening, or non-classical wave interference in gravitational wave signals, clues we might one day detect with ultra-sensitive instruments like LISA, which is Laser Interferometer Space Antenna. But all of this happens without direct interaction. Graviton condensates don't emit, absorb, or reflect light. They don't couple to electromagnetic fields. They can't be seen in radio, X-ray, or gamma-ray images. They don't leave fingerprints. They leave footprints, invisible dents in the road that everything else steps into unaware. And this makes them devilishly difficult to detect, but profoundly important. They would be everywhere and nowhere, influencing matter without ever touching it, bending light without ever being seen, guiding the cosmos not like an invisible hand, but like a silent rewriter of the rules by which everything else moves. And yet their very non-interaction with matter is what makes them such compelling candidates for explaining phenomena currently attributed to dark matter. They do what dark matter is supposed to do, add gravity without light, but they do so by reshaping the geometry of the universe, not by filling it with hidden particles. In this vision, the interaction between graviton condensates and normal matter is not of contact or collision. It is the interaction of structure with movement, of geometry with path, of curvature with time. It's the gravitational equivalent of a river shaping the course of a canoe, not through force, but through flow.
And perhaps one day, by watching the canoes closely enough, the paths of stars, the trails of photons, the rhythms of pulsars, the signals of gravitational waves, we'll find patterns, mismatches, echoes, and shifts that tell us there is something invisible here, bending space, altering time, changing the way the universe breathes. If graviton condensates are real, these vast, massless clouds of quantum gravity that bend space-time and sculpt the motion of galaxies, then the inevitable question becomes, how could we ever detect them? If they emit no light, absorb nothing, and carry no mass in the classical sense, then how can something so powerful remain invisible? The answer lies in their very nature. Graviton condensates are not things in the traditional sense. They are geometries, structures, patterns of gravitational curvature that shape everything around them. And while we may never see them directly, we might trace their shadows, not the darkness of absence, but the distortions they imprint on the behavior of everything they touch. Let's begin with perhaps the most powerful tool in modern astrophysics, gravitational lensing. In general relativity, light bends around massive objects because space-time itself is curved. We see this in action when the light from distant galaxies arcs around galaxy clusters, creating arcs, rings, or multiple images, a cosmic optical illusion caused by gravity. Astronomers have used these gravitational lenses to map invisible mass, revealing the presence of dark matter that would otherwise remain hidden. Now imagine the same scenario, but without mass. What if a region of space, completely devoid of any stars, gas, or galaxies, produces a subtle lensing effect? What if light from a distant quasar arrives a fraction of a second earlier than it should, or arcs slightly when passing through empty space? This would be a smoking gun for graviton condensates. Unlike traditional lenses formed by clumps of dark matter or ordinary mass, a lens caused by a graviton condensate would be smooth, diffuse, and perhaps strangely shaped. It might not follow the usual signatures of mass distribution.
Instead, it would warp light as though space-time itself were woven differently in that region. A distortion not caused by mass, but by massless gravitational coherence. Already, gravitational lensing surveys have hinted at dark lenses, regions where light bends more than expected, but no visible mass is present. Most of these are attributed to clumps of dark matter, but what if some are actually signatures of graviton condensates? Then there's the matter of stellar orbits. One of the clearest signs of hidden mass in the universe comes from the movement of stars, particularly those on the edges of galaxies. In a Newtonian universe, a star farther from the galactic center should orbit more slowly. But in many galaxies, stars orbit at constant speeds, even far from visible mass. This led to the idea of dark matter halos, but graviton condensates offer a new explanation: curved spacetime without mass. If we could measure stellar orbits with ultra-high precision, we might detect subtle deviations, orbital precessions, speed variations, or anomalies in velocity dispersion that don't match predictions based on visible matter. If those deviations can't be explained by dark matter particles or gas distributions, they might instead point to the presence of coherent gravitational fields, graviton condensates stretching invisibly across the galaxy. Nearby stars in our own Milky Way galaxy, like those orbiting Sagittarius A at the center of the galaxy, are already being tracked with incredible accuracy. If their paths deviate from what general relativity predicts, without enough visible or dark matter to account for the shift, it could hint at a gravitational distortion with no material cause, a signature of a condensate. Now turn your gaze to one of the newest frontiers in physics: gravitational waves. Ripples in spacetime caused by massive accelerations, merging black holes, colliding neutron stars, gravitational waves stretch and squeeze space as they move. Detectors like LIGO and Virgo have already confirmed these waves exist, and future observatories like LISA will measure them with even greater sensitivity. But what happens when a gravitational wave passes through a graviton condensate? Because the condensate is not just passive space, but a quantum-structured gravitational field, it could alter the wave as it passes through. Think of a sound wave passing through a cave. It echoes, it reverberates, it interferes with itself. A gravitational wave moving through a condensate might scatter, delay, or interfere with itself in detectable ways. This might produce echoes in gravitational wave signals, secondary pulses following the main event, not caused by the source but by wave reflection or scattering inside a condensate. Amplitude modulation, where the wave is dampened or amplified as it interacts with the quantum geometry of the condensate. Frequency shifts, where the waveform changes subtly, as though refracted by the condensate's internal structure. So far, gravitational wave signals have been clean, but as our detectors improve and more data accumulates, anomalous features might emerge, subtle deviations from the expected chirp pattern. If these deviations consistently appear in certain sky regions or in waves from certain distances, they could indicate the presence of unseen gravitational structures along the line of travel. Moreover, simulations suggest that if a black hole merger occurs within or near a graviton condensate, the resulting wave might carry non-classical features, modulations or distortions that deviate from the template patterns used to detect standard events. This could open a new class of gravitational wave signatures, events shaped not just by the objects involved, but by the gravitational medium in which they occur. Another speculative detection method involves pulsar timing arrays.
Pulsars, rapidly spinning neutron stars, emit incredibly regular pulses of radio waves. The timing of these pulses is so precise that even a minuscule perturbation in spacetime can cause a detectable shift. If a graviton condensate drifts between us and a pulsar, or if Earth moves through one, the pulse timings might drift, jitter, or exhibit strange patterns that defy explanation. Some anomalies have already been seen in pulsar timing data, though no conclusions have been drawn.
With future telescopes like the Square Kilometer Array, or SKA, the precision of pulsar observations will increase dramatically. We might then discover timing shifts correlated across multiple pulsars, forming a map of subtle gravitational variations not explained by mass, a possible fingerprint of graviton condensates. In total, the search for graviton condensates may require a multi-pronged approach, combining gravitational lensing surveys to find regions that warp light but contain no mass, high-precision orbital tracking to identify unaccounted-for gravitational influences, gravitational wave pattern analysis to reveal deviations caused by structured geometry, and pulsar timing variations to catch minute space-time distortions on galactic scales. The beauty of this strategy is that it doesn't require us to find particles. It asks us to listen for patterns, watch for curves, and measure the subtle whisper of invisible geometry across the cosmic stage. The challenge is great. The evidence, if it exists, will be faint, partial, and hard to separate from noise. But the reward is nothing short of revolutionary. The first confirmation that gravity itself can organize into structures, that the universe may be shaped not just by what is present, but how space itself has chosen to dance. Now we come to one of the most elegant and eerie implications of graviton condensates: gravitational lensing without mass. In a universe governed by Einstein's general relativity, the bending of light is a direct consequence of space-time curvature. Traditionally, that curvature is caused by mass: planets, stars, galaxies, black holes. The more massive the object, the more space bends around it, and thus the more light veers from its straight path. But graviton condensates flip this expectation on its head. They offer the possibility of curved spacetime in the absence of mass, generated purely by the coherence of gravity itself. Which raises an astonishing possibility. Could we detect gravitational lensing effects in regions where no mass is present? Let's unpack this. Gravitational lensing is not new. It's been used extensively to map the large-scale structure of the cosmos. We've seen galaxies distorted into arcs and rings. We've detected weak lensing, where light from distant galaxies is slightly sheared due to intervening dark matter. We've even measured lensing in the cosmic microwave background, the afterglow of the Big Bang. In all of these cases, the lensing has always been attributed to massive objects, often dominated by dark matter. But if graviton condensates exist, and if they can create regions of spacetime curvature without mass, then we should expect regions of unexplained lensing, places where light bends and magnifies despite the absence of any visible or inferred matter. Imagine a telescope trained on a patch of sky. In the center of this view is a background quasar, a bright, distant light source. Suddenly, the quasar appears slightly brighter, or its shape distorts subtly. Yet when astronomers search the region for galaxies, gas, or any object that could explain the lensing, they find nothing. This would be an anomaly in the standard cosmological model, but in the graviton condensate framework, it's a prediction. The gravitational lensing in this case would not come from a clump of hidden particles, but from a smooth, coherent distortion in space-time itself, shaped by the configuration of a graviton condensate. The photons from the quasar would travel through a region where space-time is subtly warped, not by mass, but by quantum coherence of the gravitational field, and their paths would bend accordingly. This lensing would have unique signatures. For one, the mass-to-lensing ratio would be off. In a typical lensing scenario, we can estimate the amount of mass responsible by analyzing how much the background light is bent. But if the actual mass in the region is negligible, yet the lensing is significant, that would suggest a new source of curvature. It would force us to question our mass-centric view of gravity. Second, the shape of the lens might be unusual. Mass-based lensing tends to produce elliptical or circular distortions, depending on the geometry of the mass distribution. A graviton condensate, on the other hand, might produce non-classical patterns, lensing effects that don't correspond to any reasonable mass configuration. There could be asymmetries, ripples, or even rotational distortions if the condensate itself possesses internal dynamics or spin-like coherence. Third, the lensing might be time variable. Unlike a galaxy, which maintains relatively stable mass over long timescales, a graviton condensate could evolve, its quantum coherence shifting, its geometry fluctuating slightly. This could cause micro-variations in the observed lensing effect over months or years. Imagine a gravitational lens that subtly changes its focusing power, not because matter moved,
but because space-time's quantum structure shifted. This opens the possibility of identifying condensates through long-term monitoring of known lensing regions. If a lensing effect grows, weakens, or changes shape without any corresponding movement of mass, it could indicate the presence of a living, breathing patch of structured spacetime, a graviton condensate in action. There's already tantalizing evidence. Some lensing observations in deep-field surveys, like those from the Hubble Space Telescope or the Subaru Hypersupreme CAM, have shown anomalous lensing regions where the observed gravitational influence doesn't quite match the inferred mass. These are usually chalked up to dark substructures or unresolved clumps of dark matter. But what if some of them are massless lenses, projections of invisible curvature?
Future missions could put this to the test. The Nancy Grace Roman Space Telescope and the Euclid Observatory will conduct wide-field gravitational lensing surveys with unprecedented precision. They'll scan billions of galaxies, mapping the gravitational scaffolding of the universe in detail. If graviton condensates exist, they may leave behind statistical fingerprints. Regions where the gravitational lensing signal is strong, yet no dark matter halo is detectable. Moreover, the James Webb Space Telescope could contribute by examining deep-lensed systems, probing the nature of dark lenses through high-resolution spectroscopy. If a region lenses light but shows no baryonic or dark matter, the only remaining suspect might be an invisible structure of pure gravity. It's also worth considering gravitational lensing in the context of gamma-ray bursts, quasars, or supernovae. These point-like, high-luminosity objects can serve as backlights against which subtle gravitational lensing effects might be amplified. A graviton condensate drifting in front of such a source could create a transient lensing event, a temporary magnification with no accompanying object. If multiple such events occur in regions without detectable matter, the case for condensate-induced lensing strengthens. Another exciting possibility lies in machine learning. With millions of gravitational lensing images being generated, researchers are training neural networks to recognize lensing patterns. If graviton condensates create lensing signatures that are unlike traditional mass-based lenses, AI systems might identify them as outliers, patterns that don't fit existing templates. These anomalies could form the first catalog of quantum geometric lenses. Ultimately, the detection of gravitational lensing without mass could mark a fundamental shift in our understanding of the cosmos. It would be proof that gravity can bend light not just because of matter, but because of its own internal coherence. That the universe may contain invisible oceans of structured space-time, warping light like ghostly hands guiding photons on unseen paths. This vision of massless lensing invites us to reimagine the very canvas of the cosmos, not as a neutral stage, but as an active player, shaping reality through invisible patterns, whispering through warped starlight, hinting that the geometry of nothingness may be the most powerful something of all. While graviton condensates are often compared to dark matter in their ability to explain gravitational anomalies, there's another cosmic mystery that invites comparison: dark energy, the enigmatic force driving the accelerated expansion of the universe. The question is both bold and tantalizing. Could graviton condensates also be responsible, at least in part, for this acceleration? Dark energy, as we understand it, behaves unlike anything else. It doesn't clump. It doesn't dilute as the universe expands. In fact, it acts like a kind of cosmic anti-gravity, pushing galaxies apart faster and faster over time. This repulsive behavior is usually attributed to a cosmological constant or some exotic quantum field permeating space. But what if the repulsion wasn't from a mysterious energy, but from a coherent gravitational structure? Graviton condensates could, in theory, generate global-scale modifications to space-time curvature.
If these condensates formed a cosmic background field, stretching across vast distances, they might create repulsive curvature gradients, not because they push, but because the geometry they impose stretches space-time apart in a similar manner. This wouldn't require a new kind of energy. It would instead be a non-local manifestation of quantum gravity, coherent configurations of gravitons altering the expansion rate of space, perhaps in subtle, uneven ways. Unlike dark matter, which clumps, and unlike traditional dark energy, which is uniform, graviton condensates might be semi-uniform, exhibiting long wavelength fluctuations across the universe. If true, this could offer an explanation for observed tensions in cosmology, such as the discrepancy between local and early universe measurements of the Hubble constant. If the cosmic expansion is being influenced by invisible gravitational structures, rather than a static cosmological constant, it might evolve differently in different epochs or regions. In this sense, graviton condensates wouldn't just mimic dark energy, they might replace it, or reveal that what we call dark energy is actually a gravitational coherence effect on cosmological scales. One of the most unsettling predictions of general relativity is that the core of a black hole collapses into a singularity, a point of infinite density, zero volume, and undefined physics. It's a place where our equations break down and all known laws of nature cease to apply. But what if that singularity never actually forms? Instead of a paradoxical point of infinite curvature, what if the core of a black hole harbors something else? Something still extreme, still exotic, but governed by quantum gravity rather than classical breakdown. Enter the concept of graviton condensate at the heart of a black hole. In this speculative model, as matter falls inward under immense gravitational compression, rather than collapsing to a point, it transitions into a new phase, a coherent state of gravitons forming a stable condensate. This condensate doesn't require infinite density to bend spacetime. Instead, its coherent quantum structure maintains intense curvature without ever reaching the unphysical limits of a singularity. This idea isn't just poetic, it solves real problems. For one, it avoids the information paradox by replacing the undefined singularity with a structure that can, in principle, store information in quantum gravitational modes. If black hole interiors are graviton condensates, they may encode infalling data across a dense and tangled network of graviton states, opening the door to eventual information retrieval through Hawking radiation or other quantum effects. It also makes black holes more physically realistic. Instead of collapsing to mathematical absurdities, they culminate in an ultra-dense yet finite gravitational object, a self-sustaining graviton core. This core would still exert a horizon, still obey thermodynamic laws, but it would be structured, not singular. Some theories like the fuzzball proposal in string theory or non-singular loop quantum gravity black holes support this view. Graviton condensates might be the missing piece, the quantum glue replacing classical infinity with finite curvature built from massless quanta of gravity. In this view, the most extreme objects in the cosmos aren't infinite points, but pure geometry made stable. A graviton cloud so dense, so coherent, that it becomes a gravitational engine unto itself. If graviton condensates exist today, bending light and shaping galaxies without mass, then a natural question arises. When did they first form? Could they be primordial? Not born in the quiet reaches of galactic outbursts, but in the turbulent, high-energy moments just after the Big Bang?
In the early universe, everything was extreme. Temperatures and densities were unimaginable. The four fundamental forces may have been unified, and particles constantly flickered into and out of existence in a quantum froth. It was a time when gravity was not the smooth, geometric field we now perceive, but a seething quantum entity dominated by fluctuations in space-time itself.
This is the perfect breeding ground for graviton condensates. Just as electrons and atoms can form Bose-Einstein condensates under the right conditions, gravitons, if they exist, might have naturally fallen into coherent quantum states during this early epoch. Tiny patches of space could have experienced resonant gravitational fluctuations, leading to the spontaneous formation of self-reinforcing graviton clouds, regions where the quantum field of gravity collapsed into a structured, coherent configuration. Once formed, these condensates could have survived the subsequent cosmic inflation, stretched to enormous scales as the universe expanded exponentially. That would mean today's graviton condensates might be fossils of the earliest phase transitions in the universe, quantum scars from when gravity began to separate from the other forces. Their presence during these foundational moments could have had a profound effect on cosmic structure formation. As the universe cooled and matter began to clump into proto-galaxies, graviton condensates may have acted as gravitational scaffolding, pulling in baryonic matter, seeding the locations of future galaxy clusters, and even influencing the shape of the cosmic web. Where traditional models rely on dark matter halos to guide structure formation, graviton condensates could serve as an alternate gravitational backbone, requiring no exotic matter, only geometry. If true, they were not latecomers. They were there from the beginning, co-evolving with the universe, shaping its destiny not through energy, but through pure space-time design. The idea of graviton condensates influencing the universe on cosmic scales only becomes viable if they are stable, not fleeting quantum events, but persistent coherent structures that endure for billions of years. But quantum systems are notoriously delicate, so the natural question is, can graviton condensates survive across the vast timeline of the universe? Or do they decay, dissipate, or decohere over time like other quantum states? To answer that, we must look at the nature of condensates themselves. In general, quantum condensates such as Bose-Einstein condensates are fragile. They often require extreme conditions like near absolute zero temperatures and can be easily disrupted by thermal noise or interaction with their environment. But graviton condensates exist in a completely different regime. They aren't formed from material particles or confined to atomic scale systems. They're built from massless gravitons, which, if real, don't decay, don't scatter like electrons or photons, and don't couple strongly to anything but spacetime itself. In this context, graviton condensates may actually be unusually stable. Their only environment is the geometry of spacetime, which they themselves shape. If their coherence is maintained not by isolation from matter, but by the self-reinforcing nature of curved spacetime, then they could exist indefinitely, semi-permanent structures in the fabric of the cosmos. Additionally, the nonlinear nature of general relativity might actually help maintain their integrity. Gravitational fields interact with themselves. Unlike electromagnetism, where fields pass through each other, gravity curves its own field lines. This could allow a graviton condensate to form a gravitational self-trap, reinforcing its structure over cosmological timescales. Still, the question of quantum decoherence looms. Could fluctuations or quantum noise eventually cause the condensate to unravel? Possibly, but if the condensate's wavelength is on cosmic scales, then its coherence might be protected by sheer scale. In other words, the universe itself may be too large for decoherence to take hold, allowing the condensate to maintain its state across billions of years. If graviton condensates are indeed stable over the age of the universe, then some of the gravitational structures we observe today, galactic halos, voids, lensing anomalies, might not be evolving at all. That could be frozen echoes of ancient gravitational coherence, unchanged since moments after the Big Bang. Graviton condensates, by their very nature, are invisible. They don't shine, reflect, or absorb light. But that doesn't mean they're undetectable. Their presence could be revealed through how they shape the universe. So if we can't see them with our eyes or telescopes in the traditional sense, what would they look like in the data? How might their fingerprints appear in the sky? First, consider gravitational lensing maps. Telescopes like Hubble and ground-based surveys like the Dark Energy Survey already construct maps of how galaxies distort the light from background sources. In these maps, the gravitational lensing effect shows up as slight shears or magnifications, small stretches or smears in the appearance of galaxies. A graviton condensate wouldn't show up as a glowing blob or a dark void, but rather as a smooth lensing distortion, a patch of sky where background galaxies are all slightly stretched or curved in one direction, without a visible mass source to explain it. It might appear as a weak lensing anomaly or a massless gravitational shadow, a ghostly hand that gently bends the light from behind it. Some of these distortions might form symmetric ripples or non-elliptical warps, especially if the condensate has internal structure or dynamic evolution. Unlike the gravitational lensing produced by galaxies, which tends to be clumpy and aligned with luminous matter, graviton condensates might create subtle, widespread distortions in otherwise featureless regions of sky. Then there's the cosmic microwave background, the oldest light in the universe. This radiation, left over from the Big Bang, has already been mapped in exquisite detail by satellites like Planck and WMAP. However, it too can be distorted by gravitational lensing as it passes through the universe. Graviton condensates, especially if they formed early and persisted, could warp the path of CMB photons on their long journey to us. In the CMB data, this might show up as minute deflections, unusual alignments or phase shifts in the temperature anisotropies, or subtle lensing features uncorrelated with known matter distributions.
Some anomalies in the CMB, like the cold spot or strange alignments in the multipole moments, have defied easy explanation. While they may ultimately be statistical noise, a few researchers have speculated that structured gravitational fields with no associated mass could be responsible. A graviton condensate drifting through the early universe could have bent the light slightly, imprinting itself as a mild shadow or shift in the cosmic afterglow. Beyond light, we can also see gravity by watching how objects move. In systems like galaxy clusters, dwarf galaxies, and even planetary systems, motion can betray the presence of hidden gravitational fields. Graviton condensates, depending on their density and geometry, could subtly affect orbital paths, not enough to throw a planet out of its orbit, but enough to make it wobble or drift ever so slightly over centuries. These orbital irregularities might appear as unexpected precessions, tiny shifts in velocity, or long-term oscillations in systems where all known mass is already accounted for. In pulsar timing arrays or precise satellite positioning systems, these deviations could eventually stand out as repeating gravitational patterns unexplained by classical models. So, what would a graviton condensate look like? Not a glowing nebula, not a black void, but rather a soft ripple in gravitational lensing maps, a phantom distortion in the cosmic microwave background, a mismatch between observed and predicted stellar or galactic motion, a slow, silent warping of light and gravity in places where there should be none. Their visibility comes not from photons, but from patterns, from the way the universe bends, flows, and moves. To see a graviton condensate is to perceive the invisible architecture of space-time itself. Modeling graviton condensates is one of the most ambitious goals in modern theoretical physics. We're talking about simulating objects that don't exist in any laboratory, have never been directly observed, and arise from the intersection of two incompatible theories, quantum mechanics and general relativity. It's like trying to draw a picture of a color no human has ever seen, and yet, physicists are trying. The challenge is immense. Gravitons themselves are hypothetical. We have no experimental confirmation that they exist, but in quantum field theory, they are assumed to be the quantum carriers of the gravitational force, just as photons carry electromagnetism. To simulate graviton condensates, scientists must build models that allow huge numbers of these hypothetical gravitons to form a coherent, stable structure, a quantum gravitational state that mimics mass through curvature alone. This is far beyond what traditional simulations can handle. Ordinary gravitational models use classical general relativity, which treats space-time as a smooth fabric,
But to simulate a graviton condensate, researchers must treat spacetime as a fluctuating quantum field made up of discrete excitations, gravitons, interacting with one another. Some of the most advanced attempts come from approaches like loop quantum gravity, string theory, and group field theory. In these frameworks, space itself is quantized, built from discrete chunks or vibrating strings. By simulating how these quantum bits of space might organize into a coherent pattern, researchers are trying to understand whether a condensate of gravitons could emerge naturally under certain conditions. In loop quantum gravity, spacetime is represented by networks called spin networks. These are webs of quantum states that encode area and volume. Under certain conditions, it's been proposed that these spin networks can transition into condensate-like states, something akin to a graviton cloud forming a macroscopic gravitational field even without mass. Group field theory takes this idea further. It allows spacetime itself to be treated like a Bose-Einstein condensate, a fluid of quantum gravitational quanta that can undergo phase transitions. In this picture, the early universe may have emerged from a graviton condensate, and remnants of these structures might still exist in the cosmos today. In the realm of string theory, gravitons are modeled as vibrational modes of strings. Some models predict that large ensembles of these stringy gravitons could form coherent structures, stabilized by extra-dimensional effects or brain configurations. Simulations in this area often require supercomputer-scale resources operating across 10 or 11 dimensions and are designed to explore how condensate-like gravitational states might arise in compactified spaces or near black hole horizons. Even outside of these high-concept frameworks, some physicists are using effective field theory to build toy models of graviton condensates. These models simplify the math by treating the condensate as a classical field with quantum corrections, allowing researchers to study its interactions with light, matter, and gravitational waves, even if they can't yet derive it from first principles. Most of these simulations remain highly abstract, limited by computational power and the lack of experimental data. But they are vital steps, laying the mathematical and conceptual groundwork for what might someday be a full quantum gravity theory. And there's one more angle: machine learning. Some researchers are using neural networks to explore non-intuitive configurations of spacetime, searching for stable quantum gravitational structures in massive datasets generated by theoretical models. AI may one day uncover novel condensate configurations, quantum gravitational objects that no human would have thought to simulate. In short, the effort to simulate graviton condensates is like simulating a future discovery. It's not just about confirming a theory, but it's about inventing new ways to think about reality itself, with the hope that the universe, in its deep structure, reflects the strange, beautiful equations we're just beginning to write. The black hole information paradox has haunted physics for decades. At its core is a fundamental contradiction. According to quantum mechanics, information can never be truly lost. But according to classical general relativity, anything that falls into a black hole, including all the information about its quantum state, is gone forever behind the event horizon. When the black hole evaporates via Hawking radiation, it seems to disappear without returning that information, violating one of quantum theory's most sacred rules.
This is where graviton condensates could offer a way out, a quantum gravitational mechanism for storing or redistributing information that avoids the paradox altogether. Imagine that instead of collapsing into a true singularity, the core of a black hole transforms into a graviton condensate, a densely packed, coherent state of quantum gravitons. This condensate wouldn't be an undefined point of infinite density, but a finite structure of pure gravitational geometry. And crucially, it would possess internal degrees of freedom, modes of oscillation, coherence patterns, or topological configurations that could encode information. When matter or energy falls into the black hole, its quantum information wouldn't be destroyed. Instead, it might be absorbed into the condensate's internal quantum state, stored within the delicate balance of graviton interactions. The event horizon would still appear to an outside observer, but behind it would be not a singularity, but a complex quantum object,
a gravitational memory bank. This concept aligns with recent proposals like the soft hair hypothesis, which suggests that information is stored in subtle features of the black hole's horizon geometry. But graviton condensates could extend this idea to the entire core of the black hole, not just its surface, but its very interior, filled with structured quantum geometry capable of maintaining entanglement and coherence over vast timescales. Moreover, if graviton radiation interacts, even weakly, with the graviton condensate, then information could leak back out over time, not through direct particle release, but through quantum interference patterns or entanglement swapping with outgoing radiation. This would preserve unitarity, the rule that quantum information must be conserved, while explaining why the radiation appears thermal until we analyze it in enough detail. Another possibility is that graviton condensates may distribute information non-locally. If these structures are connected across space-time via quantum entanglement or wormhole-like topologies, as some speculative theories suggest, then information falling into one condensate could be transferred elsewhere, not lost but moved, perhaps even to the edge of the universe. In this scenario, graviton condensates would act as quantum bridges, nodes in a hidden information network woven through space-time itself. They wouldn't just solve the information paradox, they'd point toward a new model of the universe where geometry is dynamic, quantum, and deeply communicative. In the rich mathematical tapestry of string theory and brain cosmology, gravitons are not just speculative particles, they are essential players. In these frameworks, the universe isn't just a four-dimensional arena of space and time. It could have 10, 11, or more dimensions, most of them curled up or hidden from our view. And in this vast multi-dimensional reality, the concept of graviton condensates begins to take on new forms. In string theory, all fundamental particles, including gravitons, are modeled as vibrational modes of one-dimensional strings. A graviton, in particular, arises as a closed string vibrating in a specific pattern, and it is unique because it can move freely through the extra dimensions. Unlike many particles, which are bound to the 3D brain, our familiar universe, gravitons can travel through the higher dimensional bulk, the space beyond our observable reality. This property opens the door to the possibility that graviton condensates might not even form within our visible universe, but in the higher dimensional space surrounding it. These condensates could take the shape of higher dimensional objects, membranes, tubes, clouds, or even wrapped geometries existing in the bulk, but casting a gravitational influence into our 3D brain. In this view, we might be seeing only the shadow or projection of the condensate's full structure, while its true geometry stretches into dimensions we cannot observe directly. In brain cosmology, the universe is viewed as a 3D membrane or 3-brain floating in a higher dimensional space. Gravity, and particularly gravitons, are often the only force allowed to interact with the bulk. This suggests a scenario where graviton condensates exist entirely in the bulk and yet still shape the evolution of our universe by leaking gravitational curvature into our brain. This could explain why some gravitational effects in our universe, like the apparent presence of unseen mass or the expansion of space, don't correspond to local sources. The true gravitational source could be a condensate hovering just outside our universe, influencing it through higher dimensional warping. String theory also introduces the concept of D-branes, multi-dimensional surfaces on which strings can end. In some models, graviton condensates may form on or between these branes as localized gravitational objects, not unlike black holes, but made purely from coherent graviton modes. These objects may even appear as black branes, smeared-out gravitational fields stretching across multiple dimensions. Furthermore, the presence of extra dimensions allows new mechanisms for graviton condensation. In standard 4D spacetime, gravitons have limited modes of interaction, but in higher dimensions, they can entangle, orbit, and form bound states in ways not possible in our low-dimensional view. This opens the possibility for stable condensates with rich internal structure, quantum geometries that are fundamentally extra-dimensional in nature. So, if graviton condensates are real, string theory and brane cosmology not only support their formation, but suggest that we may be only perceiving a fraction of what they truly are. These condensates could be multi-dimensional creatures pressing against the fabric of our reality, shaping our cosmos not with mass, but with the geometry of dimensions we cannot yet see. If graviton condensates are real, these massive, invisible, geometry-shaping entities that bend light and affect motion without having mass, then a wild but fascinating question naturally follows. Could we be living inside one? Could our entire solar system be gently floating within a vast, silent cloud made purely of gravitons, an immense gravitational structure that we can't see, touch, or directly measure? It's a question that straddles the line between theoretical physics and science fiction, but it's worth taking seriously. If graviton condensates can span galactic scales, if they are stable over billions of years, and if they don't emit or interact with electromagnetic radiation, then they could be everywhere, not just surrounding galaxies, but pervading space itself. If we were inside such a structure, what would it feel like? Would there be a dramatic tidal pole? A strange warping of time? Probably not. The hallmark of a graviton condensate is that its effects are gravitational and subtle. Rather than behaving like a storm, it would be more like a currentless ocean, shaping the paths of planets and light, influencing long-range motion, but doing so in a smooth, gentle, and nearly imperceptible way.
And that's the key. We might not even know. Imagine trying to detect wind while standing inside a sealed, still submarine. No pressure, no movement. Everything around you is stable. Yet from the outside, someone might see your vessel drifting with invisible currents. In a similar way, a graviton condensate might not produce any local anomalies that we could detect with traditional instruments. The solar system's internal motions would all appear normal. But from a cosmic perspective, we might be orbiting through curved space-time geometry shaped by a vast condensate. There might be subtle clues, though. For example, if we measured the solar system's acceleration relative to nearby stars or background galaxies, and if that motion didn't align perfectly with known gravitational sources, we might begin to suspect an invisible field shaping our trajectory. Or if long-term measurements of planetary orbits revealed tiny deviations, precessions, or drifts that can't be explained by general relativity or known matter, then a graviton condensate might be a candidate explanation. Even our measurements of gravitational waves could be influenced. If Earth is embedded in a graviton condensate, incoming waves might be slightly filtered, slowed, or distorted as they pass through this structured space-time. The timing of wave arrivals, their amplitude or polarization could carry minute fingerprints of the condensate's geometry. It's even conceivable that the very smoothness of our local cosmic environment, the apparent emptiness between stars and galaxies, could be due in part to graviton condensates. Rather than being truly empty, this space might be structured, laced with quantum coherent gravitational fields that guide matter, prevent clustering, or stabilize orbits on vast scales. So, are we swimming in one? It's possible. We might be orbiting inside a continent of pure curvature, a place where space-time itself is shaped not by stars or black holes, but by the collective coherence of gravitons. And we might never know unless we learn to see the shape of gravity itself, to trace the silent, invisible patterns that cradle us from every direction. If graviton condensates truly exist, massless, invisible clouds made of pure gravitational influence, then they wouldn't just shape space, they'd also bend time. Just as traditional gravity from stars and black holes can slow down time near their massive centers, a graviton condensate, composed entirely of gravity itself, could distort the passage of time in strange and subtle ways. To understand this, we have to return to one of Einstein's most astonishing insights. Gravity is not a force pulling on objects, it's the curvature of space-time itself. The stronger the gravitational field, the more space is warped,
and the slower time ticks relative to a distant observer. We see this clearly in GPS satellites. Their clocks run faster in orbit than they do on Earth's surface because they're in a weaker gravitational field. Now imagine a graviton condensate, not made of mass, but producing a coherent, large-scale gravitational field through its collective graviton structure. If such a field can mimic the space-time curvature of ordinary matter, then time itself may flow differently inside or near the condensate, even though there's no visible mass to blame. In regions where the condensate's field is denser, clocks might tick slightly slower than in more dilute regions, creating gravitational time gradients across space that have no corresponding source of mass. This could lead to incredibly subtle but cumulative effects over cosmic distances or eons of time. Even more intriguingly, if the condensate isn't static, if it fluctuates, breathes, or evolves, it could create temporal ripples, minute, ever-shifting variations in time flow that alter the evolution of local systems. Perhaps in the deepest cosmic voids, time stretches more freely, while near dense graviton condensates, the universe quietly lags, forming temporal pockets across the cosmic landscape. On a galactic scale, this might influence the formation of stars, the aging of stellar populations, or even the dynamics of dark energy. Two galaxies at the same distance might appear to evolve differently, not because they formed at different times, but because time flows differently within each galaxy's local gravitational framework, subtly tuned by graviton condensates embedded within. If graviton condensates do warp time like this, it could explain some of the mysterious timing irregularities we observe, such as the apparent discrepancies in Hubble constant measurements or unexpected variances in supernova aging curves. It might even influence the propagation of gravitational waves, causing them to stretch or contract in duration depending on the gravitational fabric they traverse. From a human perspective, the effects would be impossible to notice without the most precise atomic clocks. But cosmically, over billions of years, these minute distortions in time could sculpt the very evolution of the universe, acting as a hidden temporal architecture that shapes history not through force, but through the pace of becoming.
In this view, a graviton condensate is not just a cloud of gravity. It is a temporal lens, bending time itself, stretching or slowing the clockwork of reality in ways that no mass ever could. What if we've been asking the wrong question all along? For decades, we've hunted for dark matter, this mysterious, invisible substance we believe makes up most of the mass in the universe. We've sent satellites into orbit, built underground detectors shielded in silence, sifted through collisions in particle accelerators, and traced the dance of galaxies as they spiral faster than they should. Yet still, no direct detection, no particle, no interaction. Just shadows, just gravity. But what if the explanation isn't matter at all? What if the invisible hand shaping the cosmos isn't made of particles hiding in the dark, but of gravity itself, layered, structured, and more complex than we ever imagined? What if the missing mass is actually missing understanding, a veil not of substance, but of geometry? Graviton condensates challenge our most basic assumptions. They suggest a universe filled not with unseen things, but with unseen fields, ripples of space-time that don't come from mass, but from quantum coherence. Fields that bend light without mass, slow time without atoms, and bind galaxies not with weight, but with shape. We've always assumed that to explain cosmic anomalies, we must add something to the universe: dark matter, dark energy, exotic particles. But graviton condensates ask us instead to look deeper into what's already there: gravity, not as a passive backdrop, but as a dynamic quantum structure that might be the answer. So we leave you with this final mystery. What if the universe is not filled with hidden matter, but with hidden gravity? What if space itself is alive with structure, resonating with silent coherence, and we are merely passengers floating through a vast, invisible ocean of warped geometry. Maybe we are not just shaped by gravity, maybe we are immersed in it. Always. Everywhere. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.